Right now, as you're listening to these words, there's another version of yourself making completely different choices in a realm that exists just beyond the boundaries of our reality. Across infinite dimensions, countless copies of Earth are spinning through space, each one containing people who look exactly like you but living lives so dramatically altered that you wouldn't recognize your own existence. Some of these alternate selves might be discovering cures for diseases that plague our world, while others could be facing catastrophes we've never imagined. This isn't fantasy or wishful thinking. This is cutting-edge science suggesting that our entire cosmos, with all its magnificent galaxies and mysterious dark matter, represents merely one bubble floating in an endless sea of parallel dimensions. Every breath you take, every decision you make, every quantum particle dancing through space might be creating new branches of reality where different outcomes unfold simultaneously. Scientists working at the absolute forefront of theoretical physics have uncovered mathematical evidence pointing towards something so mind-bending that it challenges everything humans have believed about existence itself. We're about to explore territories where mathematics meets mystery, where laboratory experiments hint at truths stranger than any science fiction writer has ever dared to conceive. Tonight's journey will take us through discoveries that emerged from solving cosmic puzzles, where brilliant minds wrestling with fundamental questions about space and time accidentally stumbled upon evidence for infinite worlds. These researchers weren't looking for parallel dimensions mission, they were simply trying to understand why our universe appears so perfectly balanced, why the fundamental forces seem precisely calibrated to allow stars, planets, and life to exist at all. But before we venture into these mind-expanding concepts, I want to invite you to become part of our exploring community. If these profound questions about reality capture your imagination, showing your support through likes and subscriptions helps us continue bringing you the most fascinating discoveries from the frontiers of human knowledge. Now let's begin unraveling one of the greatest mysteries ever contemplated by scientific minds. The foundation of our story rests not on speculation but on rigorous mathematics, emerging from humanity's deepest understanding of quantum mechanics and cosmic evolution. Unlike fictional portrayals of alternate dimensions, the theories we'll examine tonight arise naturally from equations that successfully predict observable phenomena in laboratories worldwide. These concepts represent logical extensions of physics that have already proven their accuracy through countless experiments and observations. Our adventure starts with recognizing a humbling truth about the boundaries of human perception. When darkness falls and stars become visible overhead, you're witnessing only an infinitesimally small sample of what actually exists throughout space. The cosmic horizon limits our vision not because of atmospheric interference or technological limitations, but due to fundamental constraints imposed by light's finite velocity and our universe's 13.8 billion year history. Consider this perspective. Standing on any beach, Earth's curvature prevents you from seeing distant shores that definitely exist beyond the horizon. Similarly, cosmic expansion and light speed barriers create an observational boundary hiding vast territories of space-time that stretch far beyond anything telescopes can detect. Within our observable domain lie approximately 2 trillion galaxies, each containing hundreds of billions of stars surrounded by planetary systems that could harbor unimaginable diversity of worlds. Yet according to emerging multiverse theories, this incomprehensibly enormous region might constitute an infinitely small fraction of total reality. Imagine discovering that what seemed like an entire ocean was actually just a microscopic droplet within a boundless cosmic sea. This analogy barely captures the scale we're discussing, where our everything becomes virtually nothing compared to the fuller picture. The scientific groundwork for these revolutionary ideas crystallized during the 1980s, when physicist Alan Guth tackled perplexing inconsistencies within Big Bang cosmology. Traditional models predicted that our universe should exhibit significant curvature and temperature variations across different regions, yet observations revealed remarkable uniformity and flatness that seemed to violate basic physical principles. How could distant areas of space that never had opportunities to exchange information develop nearly identical properties? Guth's breakthrough solution introduced cosmic inflation use, a brief period of exponential expansion occurring during the universe's first fractional seconds. Throughout this epoch, a region smaller than atomic nuclei expanded to cosmic proportions faster than light itself could travel. This rapid stretching eliminated initial irregularities while creating the flat, uniform cosmos we observe today. However, detailed analysis of inflationary mechanisms revealed something extraordinary and unsettling. The quantum fluctuations responsible for ending inflation in our cosmic neighborhood would produce different effects across other regions of space-time. While inflation ceased here, allowing matter and energy to condense into galaxies and stars, it would continue indefinitely in other areas, eventually spawning new inflationary domains destined to undergo their own creation events. This process, termed eternal inflation, suggests our universe represents just one bubble within an endlessly expanding multiverse structure. New cosmic domains constantly emerge as quantum variations trigger inflation's termination in different regions. Each bubble universe evolves independently, developing unique physical laws and matter distributions completely isolated from all others. André Linde, among inflation theory's primary architects, describes this scenario using almost mystical language. Rather than a single cosmos governed by uniform physical principles, eternal chaotic inflation predicts a self-reproducing, perpetually existing multiverse where every conceivable possibility gets realized somewhere across infinite domains. He proposes that another version of you exists at this very moment, reading identical words in a cosmos matching ours down to quantum details. Meanwhile, in yet another dimensional bubble, Earth's history unfolded along different pathways. Perhaps asteroid impacts never eliminated dinosaurs, or entirely alternative evolutionary processes generated life forms beyond current imagination. The mathematical framework supporting eternal inflation carries both beautiful and terrifying implications for understanding reality's true nature. If these theories prove accurate, then everything capable of happening will happen not merely once, but infinitely many times throughout the vast ensemble of bubble universes. Every possible atomic arrangement, every potential quantum outcome, every conceivable variation of physical constants gets realized somewhere within the multiverse structure. This connects directly to cosmology's most puzzling mystery, the fine-tuning problem. Nature's fundamental constants, from gravitational strength to electron mass, appear precisely calibrated to permit star formation, planetary development, and ultimately biological complexity. Altering any of these values by tiny amounts would create sterile universes incapable of supporting the intricate chemistry required for life processes. Within single universe scenarios, such fine-tuning demands either extraordinary coincidence or intentional design. But throughout a multiverse populated by bubbles containing different physical properties, fine-tuning becomes a natural selection effect. We observe life-permitting constants not because they were specially chosen, but because conscious observers could only evolve within universes where such conditions happen to exist. The vast majority of multiverse domains might remain empty and lifeless, but observers can only emerge within the minute fraction where circumstances prove suitable for complexity and consciousness. This anthrope reasoning has generated intense debate among physicists, with some embracing it as an elegant solution while others view it as abandoning traditional scientific goals of finding unique predictive theories. These alternate realities exist with absolute authenticity, yet remain permanently separated from one another, creating an impenetrable barrier that prevents any form of communication or transportation between dimensional branches. The magnitude of reality splitting within quantum interpretations defies human comprehension entirely. According to Max Tegmark from Massachusetts Institute of Technology, every conceivable state manifests simultaneously at each moment throughout time. Every quantum transformation occurring within each stellar core across every galactic cluster throughout the most distant regions of space continuously divides our local existence into innumerable duplicates. The quantity of parallel dimensions expands exponentially with every passing instant, generating an incomprehensibly massive collection of realities where every potential version of historical events plays out completely. This quantum multiverse functions according to fundamentally different mechanisms compared to the bubble cosmos produced by eternal inflation processes. While inflating bubbles remain separated through physical distances and develop under potentially distinct physical principles, the numerous worlds emerging from quantum mechanics occupy identical spatial coordinates but exist in isolation due to quantum reality's inherent structural properties. They constitute separate branches within the universal wave function, each possessing equal validity and completeness as our directly experienced dimension. String theory represents physics' most ambitious endeavor to merge all fundamental forces within a unified theoretical structure, contributing its unique multiverse variation through what scientists term the string landscape. String theory demands additional spatial dimensions extending beyond the three we perceive directly. These supplementary dimensions must undergo compactification or curl up in configurations that remain concealed at ordinary scales of observation. The mathematical sophistication of string theory permits compactification through an astronomically large number of methods, with each approach producing different physical laws and constants within the resulting four-dimensional cosmos. Present calculations indicate that possible string theory vacua might reach approximately 10 raised to the 500,000th power or even higher values, establishing what Leonard Susskind describes as an enormous landscape containing possible universal configurations. When merged with eternal inflation concepts, the string landscape implies that various multiverse regions settle into distinct string theory arrangements, producing bubble dimensions with dramatically contrasting physical characteristics. Some domains might possess enhanced or diminished forces, alternative quantities of particle categories, or completely different dimensional architectures. This framework offers another plausible explanation for our cosmos's fine-tuning characteristics, with every possible value of physical constants becoming realized somewhere throughout the landscape of possibilities. Despite decades of theoretical advancement and progressively sophisticated mathematical structures, the multiverse concept remains among contemporary physics' most disputed ideas. The primary obstacle involves observational verification. By fundamental definition, alternative universes exist beyond our cosmic boundaries, or within parallel quantum branches that we cannot directly access. This apparent inability to test these theories has prompted certain critics to claim that multiverse concepts venture past legitimate scientific boundaries into metaphysical territory. The discussion addresses profound philosophical inquiries regarding scientific knowledge's essential nature. Traditional scientific methodologies emphasize creating testable predictions that can undergo verification or disproof through observation and experimentation. However, multiverse theories seem to contradict this principle by asserting claims about entities that may be inherently unobservable. Several physicists have responded by creating novel approaches for evaluating theories incapable of direct testing. They concentrate on explanatory capacity, mathematical coherence, and the ability to generate predictions about observable phenomena, even when the theory references unobservable entities. Others maintain deep skepticism, contending that without empirical contact, these concepts cease functioning as physics and transform into something resembling philosophy or pure mathematics. The quest for evidence has guided scientists toward examining delicate patterns within cosmic microwave background radiation, the ancient electromagnetic energy remaining from when our universe existed for merely 380,000 years. Researchers have searched for signatures potentially indicating collisions with alternative bubble universes, unusual correlations suggesting quantum entanglement between different reality branches, or statistical irregularities deviating from single universe predictions. One especially fascinating characteristic involves the cosmic microwave background cold spot, an extraordinarily large and frigid region within the Eridanus constellation that seems to contradict standard cosmology statistical expectations. Some investigators have theorized that this anomaly might constitute evidence of interaction with another dimensional realm, though more conventional explanations involving supervoids and gravitational influences remain preferred by most scientists. The consequences in this debate could not be more significant. If multiverse theories prove accurate, they would completely revolutionize our comprehension of reality, indicating that our observable cosmos represents merely one strand within an infinite fabric of existence. Every inquiry about why the universe possesses its particular properties would require reframing through observer selection effects across an ensemble of realities. The fundamental meaning of existence, uniqueness, and cosmic importance would demand total reconceptualization. But the ramifications extend far beyond abstract philosophical considerations into the practical domain of how scientific investigation should proceed. If we acknowledge that certain aspects of reality may remain forever beyond direct observation, how do we preserve scientific precision? How do we differentiate between legitimate theoretical speculation and untestable metaphysical claims? These inquiries challenge the scientific method's foundational principles. The experimental pursuit of multiverse indicators has driven observational cosmology to its absolute boundaries, compelling scientists to create increasingly sophisticated methods for detecting phenomena that may be fundamentally beyond direct observation. At research facilities worldwide, investigators scrutinize cosmic microwave background information with the concentration of forensic experts analyzing crime scene evidence, seeking the most subtle clues that our universe might have previously encountered another reality. Stephen Feeney and his associates at University College London generated significant attention in 2010 when they declared discovering circular formations in the cosmic microwave background that could represent scars from encounters with neighboring bubble universes. These characteristics, if authentic, would manifest as gentle temperature fluctuations embedded within the ancient light, permeating all space. The research team created sophisticated algorithms to examine millions of data points, searching for the specific geometric indicators that theoretical models predicted such encounters would produce. The analysis proved extraordinarily intricate, requiring investigators to consider countless contamination sources and systematic errors. Galactic foregrounds, instrumental interference, and natural statistical variations within the cosmic microwave background all collaborated to conceal any potential multiverse indicators. Nevertheless, when analysis concluded, Feeney's group reported discovering several candidate features matching the anticipated properties of bubble encounters with statistical significance, apparently ruling out mere coincidence. The announcement created waves of excitement throughout the cosmology community, but the enthusiasm proved temporary. More comprehensive analysis utilizing data from the European Space Agency's Planck satellite, possessing resolution 3 times superior to previous missions, failed to validate the claimed discoveries. The circular formations that had appeared so promising dissolved into statistical interference when examined with enhanced precision. The investigation had pushed the limits of what could be extracted from observational information, but it had not successfully crossed the barrier separating our universe from others. This sequence of initial excitement, followed by careful refutation, has characterized much of the empirical search for multiverse evidence. In 2015, another research group claimed identifying anomalous patterns within the cosmic microwave background that might indicate quantum entanglement between our universe and others. The investigators suggested that correlations between widely separated sky regions might reflect quantum mechanical connections that existed before cosmic inflation separated different areas into causally disconnected universes. The proposal was ingenious, building upon quantum mechanics' fundamental principles to predict observable consequences of multiverse theories. If regions of our observable universe had previously been quantum mechanically entangled with regions now existing in other bubble universes, then subtle correlations might persist in the cosmic microwave background radiation. These quantum remnants would provide a direct view into the multiverse, preserved within the most ancient light we can observe. Yet again, independent analysis failed to confirm the claimed discoveries. The correlations that had seemed significant in initial studies proved consistent with natural statistical variations expected in a single universe. The search for quantum entanglement signatures joined the expanding list of tantalizing possibilities that had not survived rigorous examination. These failures have not discouraged researchers from continuing the hunt for multiverse evidence. Instead, they have driven the development of increasingly sophisticated theoretical frameworks for predicting what signatures other universes might leave in observable phenomena. Several investigators have proposed that encounters between bubble dimensions might produce distinctive gravitational wave patterns detectable by existing or upcoming observational facilities. Advanced LIGO has successfully identified dozens of gravitational wave phenomena from merging black holes and neutron star collisions, offering unprecedented glimpses into extreme gravitational processes. Scientists scrutinize data from these discoveries for any unusual characteristics that might reveal interactions with alternate dimensions or departures from general relativity, supporting multiverse concepts. Although no conclusive indicators have emerged yet, this research field remains remarkably young, with significantly more sensitive detection equipment planned for forthcoming decades. The European Space Agency's anticipated LISA mission will position gravitational wave sensors in orbital configurations, enabling access to completely different frequency spectrums compared to terrestrial installations. These space-deployed observatories could potentially identify gravitational waves originating from the primordial universe itself, including any traces left by eternal inflation processes responsible for generating bubble dimensions. The prospect of directly witnessing the creation of alternate universes through gravitational radiation constitutes among the most thrilling possibilities within multiverse investigation. Simultaneously, the Large Hadron Collider, alongside other particle physics installations, continue exploring matter and energy's fundamental architecture at microscopic scales. Various theoretical frameworks suggest that evidence supporting extra dimensions or string theory could offer indirect validation for multiverse scenarios. Discovering additional spatial dimensions, novel fundamental particles, or unexpected symmetries within physical laws could strengthen arguments for theories naturally producing multiverse predictions. The pursuit of dark matter, comprising approximately 85% of universal matter content, has gained fresh importance within multiverse theoretical contexts. Certain models propose that dark matter consists of particles interacting primarily through gravitational forces, rendering them nearly invisible to conventional matter. If such particles exist, they might offer insights into fundamental physics underlying multiverse scenarios, particularly those involving extra dimensions or exotic particle behaviors. Underground research facilities worldwide conduct progressively sensitive searches for dark matter particles, employing detectors buried deep beneath Earth's surface for protection against cosmic radiation interference. The most advanced experiments can identify atomic nuclei recoil from dark matter encounters with precision approaching theoretical boundaries imposed by quantum mechanical principles. While no definitive dark matter discoveries have received confirmation, ongoing investigations continue constraining theoretical models and could potentially reveal new physics relevant to multiverse frameworks. The relationship between particle physics and cosmology has become increasingly crucial, as investigators recognize that comprehending the multiverse requires knowledge spanning both largest and smallest scales. The fundamental forces and particles governing laboratory interactions also determine properties of entire universes throughout the multiverse landscape. This connection has inspired development of innovative interdisciplinary approaches, combining insights from high-energy physics, cosmology, and quantum field theory. String theorists have assumed particularly significant roles in developing these connections, utilizing mathematical instruments from quantum field theory to examine both microscopic structures of fundamental particles and macroscopic evolution of complete universes. The string landscape emerges from detailed calculations determining how extra dimensions can undergo compactification through different methods, with each configuration corresponding to distinct sets of physical laws and constants. The mathematical complexity surrounding these calculations proves staggering, incorporating advanced techniques from algebraic geometry, topology, and mathematical physics. Researchers must navigate through abstract mathematical spaces containing hundreds or thousands of dimensions, charting the landscape of possible universes and determining which configurations possess sufficient stability to support long-lasting cosmic evolution. The quantity of possible configurations expands exponentially with compactification scheme, complexity, producing the vast ensemble of possibilities characterizing the string landscape. Leonard Susskind, among string theory's founding figures, has emerged as a prominent advocate for the anthropic approach toward understanding this landscape. From his perspective, the tremendous number of possible string theory vacua naturally explains apparent fine-tuning of physical constants within our universe. Rather than requiring special initial conditions or intelligent design, fine-tuning emerges from observer selection effects across the enormous ensemble of possibilities. This anthropic reasoning carries profound implications for understanding theoretical physics objectives and methodologies. Traditionally, physicists have pursued theories generating unique testable predictions about observable phenomena. The discovery of quantum mechanics, relativity, and the standard model of particle physics all followed this pattern, with theoretical developments producing specific experimental predictions suitable for verification or refutation. However, the string landscape suggests alternative approaches where theories predict not unique outcomes, but probability distributions across ensembles of possibilities. Within this framework, physics' goal becomes understanding which universe types appear more frequently in the multiverse and calculating probabilities that observers resembling ourselves would encounter universes with specific properties. This transition toward probabilistic reasoning has generated intense controversy throughout the physics community. Critics contend that anthropic explanations remain inherently untestable and therefore unscientific. They express concerns that accepting anthropic reasoning could lead to abandoning searches for deeper, more fundamental explanations regarding why the universe possesses its observed characteristics. Supporters respond that anthropic reasoning has already demonstrated success in generating testable predictions. They reference cases where anthropic arguments correctly predicted the observed cosmological constant value ms, the energy density of empty space, driving accelerating universal expansion. Steven Weinberg employed anthropic reasoning during the 1980s to predict that the cosmological constant should remain small yet positive, a prediction dramatically confirmed through distant supernova observations in the 1990s. The cosmological constant represents among physics' most severe fine-tuning problems. Quantum field theory predicts that empty space should possess enormous energy density roughly 10 to the 120th power times larger than observational evidence indicates. This discrepancy represents the worst theoretical prediction in scientific history, suggesting that our understanding of quantum mechanics, general relativity, or both must be fundamentally incomplete. Within single universe scenarios, explaining why the cosmological constant maintains its observed value requires either extraordinary fine-tuning or completely novel physics. But throughout a multiverse where different spatial regions can possess varying cosmological constant values, the observed value becomes a selection effect. Universes containing large positive cosmological constants expand so rapidly that matter never condenses into galaxies and stars. Universes possessing large negative cosmological constants collapse before complex structures can develop. Only universes maintaining cosmological constants near zero permit galaxy, star, and planet formation necessary for observer emergence. This anthropic explanation for the cosmological constant has proven remarkably successful, correctly predicting the magnitude and sign of observed values years before measurement occurred. The success has encouraged researchers to apply similar reasoning to additional fine-tuning problems, from fundamental force strengths to elementary particle properties. Nevertheless, the anthropic approach raises disturbing questions about scientific explanation and prediction's essential nature. If we accept that some aspects of reality result from observer selection effects rather than deeper physical principles, how do we determine which phenomena require traditional scientific explanations versus anthropic reasoning? This question strikes at the heart of what constitutes legitimate scientific inquiry. The debate has prompted some physicists to develop new criteria for evaluating theories that incorporate anthropic elements. They argue that anthropic reasoning should supplement rather than replace traditional theoretical approaches, providing explanations for fine-tuning problems while maintaining the search for deeper underlying principles. Others remain convinced that anthropic reasoning represents a fundamental departure from scientific methodology, arguing that it abandons the goal of finding unique predictive theories in favor of statistical arguments about ensemble properties. The resolution of this debate may ultimately determine whether multiverse theories become accepted components of mainstream physics or remain speculative ideas existing at the boundaries between science and philosophy. This controversy reflects deeper tensions within contemporary theoretical physics between mathematical elegance, empirical testability, and explanatory power. As our understanding of fundamental reality grows more sophisticated, we increasingly encounter theories that challenge traditional notions of what constitutes acceptable scientific explanation. The multiverse debate exemplifies these challenges, forcing us to confront fundamental questions about the relationship between theory and observation, the role of probability in physical explanation, and the boundaries of legitimate scientific inquiry. If we acknowledge that certain characteristics of our cosmos emerge from selection effects throughout a multiverse collection, how do we differentiate between authentic predictions and retrospective explanations? How do we preserve scientific precision when addressing theories that reference fundamentally unobservable entities? These inquiries have prompted development of novel philosophical structures for evaluating theories transcending traditional empirical limitations. Several philosophy of science scholars have suggested criteria based on explanatory capacity and mathematical coherence, rather than direct testability. Others have advocated for more pragmatic methodologies, emphasizing whether theories generate successful predictions about observable phenomena, regardless of whether their underlying assumptions can undergo direct verification. The discussion has grown complex through recognizing that even our most successful theories routinely reference unobservable entities. Quarks, the fundamental components of protons and neutrons, cannot be isolated and examined directly due to strong nuclear force characteristics. Nevertheless, their existence receives universal acceptance because of quantum chromodynamics' successful predictions, the theory describing their interactions. Similarly, the Higgs boson existed solely as a theoretical concept for nearly 5 decades before detection at the Large Hadron Collider occurred. Multiverse theories differ from these examples primarily through the scale of their unobservable elements. While individual quarks or Higgs bosons cannot undergo direct observation, their collective effects can be measured through laboratory experiments. Alternative universes, by contrast, may be fundamentally beyond any possible observation or experimental reach. This difference in observational accessibility has become a central controversy point when evaluating multiverse theory's scientific legitimacy. Some investigators have responded by creating new approaches to testing multiverse theories, focusing on their observable consequences rather than their unobservable assumptions. These indirect examinations investigate whether multiverse theories make successful predictions about phenomena we can observe, such as cosmic microwave background statistical properties, galaxy distribution on large scales, or particle physics fundamental constants. The cosmic microwave background has emerged as perhaps the most significant testing ground for these indirect approaches. This ancient radiation carries information about conditions in our universe when it existed for only 380,000 years, providing a detailed snapshot of cosmic evolution at a crucial epoch. Any interactions with other universes or exotic physics associated with multiverse scenarios might leave subtle imprints within this primordial light. Advanced statistical techniques have been developed to extract every possible information fragment from cosmic microwave background data. Machine learning algorithms search for patterns that human researchers might overlook, while sophisticated theoretical models predict what signatures different multiverse scenarios should produce. The European Space Agency's Planck satellite has provided the most detailed cosmic microwave background maps ever obtained, with sensitivity approaching fundamental limits imposed by cosmic variance. Yet, despite extraordinary advances in both observational capability and theoretical sophistication, the cosmic microwave background has revealed no definitive evidence for multiverse phenomena. The radiation appears remarkably consistent with standard single-universe cosmology predictions, with only minor deviations explainable by conventional astrophysical processes. This absence of clear multiverse signatures has led some researchers to conclude that other universes, if they exist, have left no detectable traces within our observable cosmos. The isolation between different multiverse regions may be so complete that no information can flow between them, making empirical verification fundamentally impossible. Others maintain that the search has only just begun, and that future observations with more sensitive instruments might reveal subtle signatures that current technology cannot detect. The next generation of cosmic microwave background experiments, ground-based telescopes studying universal large-scale structure, and space-based gravitational wave detectors all offer new possibilities for testing multiverse theories. The James Webb Space Telescope, now operational and providing unprecedented views of the early universe, represents another potential window into multiverse physics. By observing the most distant galaxies ever detected, Webb is probing cosmic epochs that may preserve information about fundamental processes that gave rise to our universe. If eternal inflation or other multiverse mechanisms played roles in cosmic origins, their signatures might be visible within the earliest galactic structures' properties. The search for multiverse evidence has also inspired development of entirely new theoretical frameworks that could make more specific predictions about observable phenomena. Some researchers have proposed that different multiverse regions might be connected by traversable wormholes or other exotic space-time structures that could allow limited information transfer between universes. While such connections would still fall far short of direct observation, they might create detectable anomalies in matter and energy distribution throughout our universe. Other theoretical approaches focus on multiverse theory's quantum mechanical aspects, particularly the many worlds interpretation of quantum mechanics. Some researchers have suggested that subtle correlations between quantum measurements might reveal information about parallel reality branches. Though practical challenges of detecting such correlations appear enormous, quantum computing has provided new tools for exploring these quantum mechanical aspects of multiverse theories. David Deutsch, among quantum computation pioneers, has argued that quantum computers derive their extraordinary power from performing calculations across multiple parallel worlds simultaneously. If correct, this interpretation suggests we are already harnessing multiverse computational resources even if we cannot directly observe other realities. Quantum computers have successfully demonstrated ability to solve certain problems exponentially faster than classical computers, apparently by exploring vast numbers of solution paths simultaneously through quantum superposition. The mathematical description of these quantum algorithms bears striking resemblances to the many worlds interpretation, where different reality branches explore different computational pathways before converging on final answers. While this connection between quantum computing and parallel worlds remains speculative, it illustrates how multiverse theories continue influencing cutting-edge research in physics and computer science. The boundaries between theoretical speculation and practical application become increasingly blurred as our quantum mechanics understanding deepens and our technological capabilities advance. The implications of these developments extend far beyond academic physics into questions about reality's fundamental nature and our place within it. If multiverse theories prove correct, they would require us to reconceptualize almost everything we think we know about existence, uniqueness, and cosmic significance. Our entire observable universe, with its rich history of stellar evolution, galactic formation, and biological development, would represent just one small chapter within an infinite cosmic library. The profound philosophical implications ripple outward like waves in a cosmic pond, touching every aspect of how we understand meaning, purpose, and identity within an infinite multiverse. Consider what it means to be unique when there might be countless identical copies of yourself scattered across bubble universes, each living lives that diverge at different quantum decision points. In some realities, you never encountered this content tonight. In others, you became a physicist yourself, dedicating your life to unraveling these very mysteries we're exploring together. Max Tegmark of MIT has spent decades contemplating these existential puzzles. In his mathematical universe hypothesis, he suggests that all mathematically consistent structures exist as physical realities somewhere in the ultimate multiverse. This isn't just bubble universes of eternal inflation or quantum mechanics parallel branches, but every possible mathematical framework that could describe a self-consistent reality. Universes where mathematics itself operates differently, where logic follows alternate rules, where the very concept of existence takes forms we cannot even imagine. Tegmark describes this as a four-level hierarchy of multiverses, each more exotic than the last. Level 1 encompasses regions beyond our observable horizon, containing more of the same physics but different matter arrangements. Level 2 includes eternal inflation's bubble universes with potentially different physical laws and constants. Level 3 represents quantum mechanics parallel branches where all possible outcomes of quantum events are realized. And Level 4, the most speculative, contains all possible mathematical structures as physical realities. The mathematical universe hypothesis pushes boundaries of what we might consider physics versus philosophy. If every logically consistent mathematical structure corresponds to a physical universe, then abstract concepts like numbers, geometric shapes, and algebraic equations become as real as stars and planets we observe. We wouldn't just live in a mathematical universe At some sim, we would be mathematical structures, patterns of information processing within a vast computational multiverse. This perspective transforms how we think about the relationship between mind and mathematics. When you contemplate a geometric theorem or solve an equation, you might be directly interfacing with mathematical structures that constitute reality itself. Consciousness wouldn't emerge from material processes, but would represent the universe's method of exploring its own mathematical nature through self-aware information patterns. Yet, even as these theories push toward limits of human comprehension, physicists continue developing new frameworks for testing their implications. The holographic principle discovered through studies of black hole physics suggests that all information contained within any volume of space can be encoded on its two-dimensional boundary. This revolutionary insight implies that our three-dimensional reality might itself be a projection from information stored on distant cosmic boundaries, fundamentally altering how we conceptualize the relationship between space, time, and information in a multiverse context. This extraordinary concept originated from attempts to resolve paradoxes about what occurs to information falling into black holes, but its ramifications extend far beyond gravitational physics. Leonard Susskind and Gerard Hooft independently developed the holographic principle during the 1970s and 80s, demonstrating that any region's three-dimensional interior can be completely described by information stored on its two-dimensional surface. This isn't merely a mathematical technique, but reflects something fundamental about space, time, and information's essential nature. The holographic principle carries profound consequences for multiverse theories. If our three-dimensional reality is actually encoded on a distant two-dimensional surface, then the distinction between simulation and reality becomes meaningless. We might be holographic projections of information processing occurring in dimensions we cannot directly perceive. The richness and complexity of our experienced reality would emerge from quantum computations happening on the cosmic horizon, the boundary of our observable universe. Juan Maldaceno's discovery of the anti-de Sitter-Sallah conformal field theory correspondence in 1997 provided concrete mathematical realization of holographic principles. His work demonstrated that a theory of quantum gravity in higher dimensional anti-de Sitter space is mathematically equivalent to a quantum field theory on its lower dimensional boundary. This holographic duality has become among theoretical physics' most important developments, providing new tools for understanding both quantum gravity and strongly interacting quantum systems. The anti-de Sitter conformal field theory correspondence suggests that the gravitational physics we experience might be the holographic shadow of quantum field theories operating in higher dimensions. Particles, forces, and even space-time itself would be emergent properties of more fundamental information processing occurring beyond our direct perception. This holographic emergence provides yet another pathway to multiverse scenarios where different boundary theories could give rise to different bulk spacetime realities. These holographic ideas are influencing how researchers think about reality's fundamental nature. Rather than space and time being fundamental, they might be emergent properties of more basic information processing. The universe wouldn't be made of matter and energy moving through space, but of quantum information being processed according to mathematical rules that create physical reality's appearance. This information-theoretic approach to physics has gained momentum through developments in quantum computing and quantum information theory. Researchers have discovered that many of physics' most important quantity, made from black hole entropy to spacetime curvature, can be expressed in terms of quantum information. The universe begins to look less like a mechanical system and more like a vast quantum computer processing information, on scales from subatomic to cosmic. The connection between information and multiverse theories becomes particularly intriguing when we consider observation and measurement's role. In quantum mechanics, the act of observation appears to play a fundamental role in determining which possibilities become actualized. If consciousness represents a form of information processing, then observers might not just be passive witnesses to reality, but active participants in the cosmic computation that generates physical existence. This observer participatory universe concept, developed by John Wheeler and others, suggests that the act of asking questions about reality helps create the reality we observe. In a multiverse context, conscious observers might serve as the mechanism that selects which reality branch becomes experienced, navigating through the infinite tree of possibilities that quantum mechanics generates. The implications extend to questions about the multiverse's origin and ultimate fate. If realities can branch and merge through quantum processes, then the multiverse might not be static but dynamically evolving, with new universe types constantly emerging while others fade away. Some researchers have speculated about cosmological natural selection, where universes that produce black holes create offspring universes through quantum tunneling processes, leading to multiverse population evolution over cosmic time. Lee Smolin has developed this idea into a comprehensive theory called cosmological natural selection, suggesting that universes with physical constants favoring black hole formation are more likely to reproduce and pass their properties to descendant universes. Over vast timescales, the multiverse would evolve toward configurations that maximize black hole production, potentially explaining why our universe has physical constants allowing stellar collapse and black hole formation. This evolutionary approach to multiverse theory provides naturalistic explanations for apparent fine-tuning without invoking anthropic reasoning. Instead of requiring specially chosen physical constants to permit observers, cosmological natural selection suggests these constants evolve through processes analogous to biological evolution, with successful universes reproducing more frequently than unsuccessful ones. The theory makes specific predictions about properties we should observe in our universe, particularly regarding elementary particle masses and fundamental force strengths. These predictions can be tested against observations, providing potential ways to evaluate the theory's validity without directly observing other universes. Yet even these evolutionary multiverse theories face the challenge of explaining how the first universes came into existence. If new universes are born from black holes in existing universes, what created the original parent universe that started the entire process? This regression problem appears in many multiverse scenarios, suggesting that understanding cosmic origins might require concepts transcending our current frameworks entirely. Some researchers have proposed that the multiverse might be eternal and self-creating, with no beginning or end in conventional time. In these scenarios, the question of ultimate origins becomes meaningless because time itself is an emergent property of local physics rather than a universal backdrop against which events occur. Different multiverse regions might have their own local time coordinates, with no global temporal ordering that would allow identifying a moment of creation. The search for experimental signatures of these exotic multiverse scenarios continues pushing observational cosmology toward new frontiers. Cosmic microwave background polarization experiments like BICEP and Planck are searching for subtle spiraling patterns that primordial gravitational waves would imprint on ancient light. These gravitational waves, if detected, would provide direct evidence for the inflationary epoch that potentially gave birth to our bubble universe. The European Space Agency's upcoming Euclid mission will map dark matter and dark energy distribution across billions of galaxies, potentially revealing signatures of interactions with other universes or exotic physics associated with multiverse scenarios. The mission will create the most detailed three-dimensional map of cosmic structure ever attempted, providing unprecedented insight into fundamental forces shaping our universe. Ground-based telescopes are also contributing through increasingly sensitive observations of distant supernovae, galaxy clusters, and other cosmic phenomena. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire southern sky repeatedly for 10 years, potentially discovering subtle anomalies that could point toward multiverse physics. These observational programs are complemented by advances in theoretical modeling and computer simulation. Researchers are developing increasingly sophisticated models of how multiverse interactions might manifest in observable phenomena, creating detailed predictions testable against real data. Supercomputer simulations explore how bubble universes might collide and what signatures such collisions would leave in cosmic microwave background radiation. Machine learning and artificial intelligence are also being deployed in the search for multiverse evidence. Neural networks trained on theoretical predictions can search through vast astronomical datasets, identifying patterns that human researchers might miss. These AI systems are particularly valuable for detecting subtle correlations or anomalies that might indicate interactions with other universes. The international collaboration required for these searches has created new models for scientific cooperation transcending traditional boundaries. Researchers from dozens of countries contribute to experiments like the Large Hadron Collider and Laser Interferometer Gravitational Wave Observatory, pooling resources and expertise to tackle questions no single institution could address alone. This global scientific enterprise reflects the profound human drive to understand our cosmic context, regardless of whether that context includes other universes beyond our own. The search for the multiverse has pushed us to develop new technologies, mathematical techniques, and philosophical frameworks, advancing human knowledge in countless ways. Even as ultimate questions remain tantalizingly beyond our reach, the next generation of experiments and observations will provide unprecedented sensitivity to subtle signatures that multiverse theories predict. The James Webb Space Telescope is already revealing details about the earliest galaxies that formed in our universe, potentially preserving information about cosmic conditions that gave rise to our bubble of reality. Future gravitational wave detectors in space will probe space-time's fundamental structure, perhaps detecting remnants of cosmic inflation or interactions between parallel universes. Quantum computing advances are opening new possibilities for testing the many worlds interpretation through increasingly sophisticated quantum information experiments. As these systems become more powerful and controlled, they might reveal correlations or effects, providing evidence for parallel quantum realities processing information alongside our own. Yet even as technology advances and theories become more sophisticated, the fundamental challenge of observing the unobservable remains. The multiverse, if it exists, might be forever beyond direct detection, accessible only through its subtle influences on the reality we can observe. This limitation doesn't diminish the profound impact these theories have had on our understanding of existence itself. Whether or not we ever definitively prove the multiverse's existence, the journey of exploring these possibilities has expanded our conception of what reality might be and our place within it. Perhaps that expansion of human consciousness represents the most valuable discovery of all, the recognition that reality might be far stranger, far more magnificent, and far more infinite than we ever dared to imagine. In contemplating the multiverse, we touch something fundamental about human nature, our insatiable curiosity about the deepest mysteries of existence, and our willingness to push beyond the boundaries of the known into realms where science meets wonder. This constraint compels us to wrestle with deep inquiries about scientific knowledge's essence and human understanding's limitations. Perhaps multiverse theory's greatest contribution isn't their potential accuracy, but their function in broadening our conception of what might be achievable. They challenge us to think beyond our observable universe's familiar boundaries, to consider possibilities that stretch imagination while remaining anchored in rigorous mathematics and meticulous observation. In contemplating infinite realities where every possibility becomes realized, we gain perspective on our own existence's preciousness and contingency. Every decision, every moment of awareness, every experience of beauty or wonder becomes part of a vast cosmic narrative that encompasses not just our universe, but potentially all possible universes that mathematical consistency permits. Whether the multiverse exists as physical reality or remains a theoretical construct, it serves as a mirror reflecting our deepest questions about existence, meaning, and our place in the grand scheme of things. The search for other universes ultimately becomes a search for understanding ourselves and reality's nature itself, a quest that pushes human knowledge boundaries toward horizons we are only beginning to glimpse. The question of whether we will ever definitively prove other universes' existence brings us face to face with scientific knowledge's fundamental limits. As we drift deeper into these conceptual waters, we encounter something both humbling and profound. The very theories that predict the multiverse also suggest why it might remain forever beyond our direct reach. Consider the observational challenges confronting any attempt to detect other universes. The cosmic microwave background radiation represents our most ancient observable light, carrying information from when our universe was merely 380,000 years old. This primordial glow has traveled through space for over 13 billion years to reach our telescopes tonight, and it may contain the only accessible evidence of what happened during the universe's first moments. Dr. Ranga Dharmadhikari at the California Institute of Technology spent years developing new statistical techniques to analyze this ancient radiation. His work focused on detecting what he calls anomalous emissions that might indicate interactions with neighboring bubble universes. The mathematics involved are staggering in their complexity, requiring analysis of millions of data points while accounting for countless contamination sources and systematic errors. Dharmadhikari's team discovered something intriguing. Embedded within the cosmic microwave background's seemingly random fluctuations, they found patterns appearing too organized to result from purely random processes. These patterns manifested as subtle temperature variations that seem to align in ways violating standard cosmology statistical expectations. The alignments were faint, requiring extraordinary precision to detect, but they persisted across multiple independent analyses. The discovery sparked intense debate within the cosmology community. Some researchers suggested these patterns might represent gravitational influence of matter in other universes, creating subtle distortions in spacetime's fabric that would appear as temperature variations in the cosmic microwave background. Others proposed they might indicate regions where our bubble universe had brushed against neighboring bubbles during cosmic inflation. Yet skeptics pointed out that extraordinary claims require extraordinary evidence, and the patterns Dharmadhikari's team detected remain tantalizingly close to current instruments' noise level. Independent research groups attempted to verify findings using different analysis techniques and datasets, but results remained ambiguous. Some confirmatory evidence emerged, while other studies found no significant deviations from random expectations. This pattern of tentative detection, followed by inconclusive verification, has characterized much of the observational search for multiverse evidence. The phenomena we seek exist at the very limits of what current technology can measure, buried beneath layers of cosmic noise and systematic uncertainties that make definitive conclusions extraordinarily difficult to reach. Laura Mersini-Horton at the University of North Carolina has approached the problem from an entirely different angle, focusing on what she calls quantum entanglement fossils. Her theory suggests that before cosmic inflation separated different regions into causally disconnected universes, these regions were quantum mechanically entangled. Even after inflation stretched them beyond any possibility of communication, subtle correlations might persist as observable signatures in the cosmic microwave background. Mersini-Horton's predictions are mathematically precise and potentially testable. She has identified specific patterns that quantum entanglement between universes should produce in cosmic microwave background radiation's polarization. These patterns would manifest as correlations between sky regions that have never been in causal contact, creating what she describes as spooky action at cosmic distance. The European Space Agency's Planck satellite collected data with sufficient precision to test some of Mersini-Horton's predictions, and initial results showed tantalizing hints of the predicted correlations. However, as with previous claim detections, independent verification proved elusive. The signals were weak, analysis complex, and alternative explanations involving conventional astrophysical processes could not be definitively ruled out. These observational challenges have led some researchers to explore entirely different approaches to testing multiverse theories. Rather than searching for direct signatures of other universes, they focus on testing theoretical frameworks that predict multiverse scenarios. If eternal inflation theory, or the many worlds interpretation of quantum mechanics, can be verified through other means, then their multiverse implications gain credibility even without direct detection of parallel realities. This indirect approach has proven remarkably fruitful. The discovery of the Higgs boson at the Large Hadron Collider confirmed key predictions of the standard model of particle physics, lending support to quantum field theories that naturally lead to multiverse scenarios. Gravitational wave detections by LIGO and Virgo have verified Einstein's general relativity with unprecedented precision, strengthening our confidence in theoretical frameworks underlying cosmic inflation. Meanwhile, advances in quantum computing are providing new ways to test the many worlds interpretation. David Deutsch argues that quantum computers derive their computational power from performing calculations across multiple parallel worlds simultaneously. If this interpretation is correct, then every quantum computation provides indirect evidence for parallel realities' existence. Recent experiments with quantum computers have demonstrated their ability to solve certain problems exponentially faster than classical computers, apparently by exploring vast numbers of solution paths simultaneously. The mathematical description of these quantum algorithms bears striking resemblances to many worlds interpretation, where different reality branches explore different computational pathways before converging on final answers. As we stand at the threshold of even more powerful quantum technologies and unprecedented astronomical observations, we face a profound realization. The search for the multiverse has already transformed our understanding of reality, regardless of whether we ever directly observe other universes. It has pushed us to develop new mathematical tools, observational techniques, and philosophical frameworks that expand human knowledge in countless directions. The journey into multiverse theories has taught us that reality might be far stranger and more magnificent than we ever imagined. It has challenged our assumptions about uniqueness, causality, and the nature of existence itself. Whether or not infinite parallel worlds actually exist, contemplating them has opened our minds to possibilities that stretch beyond the boundaries of everyday experience. In the end, perhaps that expansion of consciousness represents the most valuable discovery of all. Through exploring the concept of multiple realities, we have discovered something profound about ourselves. These our capacity for wonder, our ability to envision possibilities beyond direct experience, and our relentless drive to understand our place in the cosmos. The multiverse remains one of the great mysteries of our time, a question that may never be definitively answered, but continues to inspire new discoveries and deeper understanding. As you contemplate these infinite possibilities spreading out across dimensions we cannot perceive, remember that you are participating in one of humanity's greatest adventures, the quest to understand the true nature of reality itself. Tonight, as you look up at the stars, consider that you might be witnessing just one small corner of an infinite cosmic tapestry, where every possibility unfolds somewhere in the vast ensemble of realities that mathematics suggests might exist. Whether those other worlds are real or remain forever in the realm of theoretical possibility, the journey of exploring them has already changed us in ways we're only beginning to comprehend. The search continues, driven by our endless curiosity and our profound desire to understand not just what we can observe, but what might be possible in the infinite expanse of existence itself. At this very moment, while you absorb these words, infinite versions of yourself exist across dimensions, making completely different life choices in realities stretching beyond anything your mind could ever comprehend. Some alternate selves discovered cures for every disease known to humanity, while others face catastrophes our world has never witnessed. This isn't imaginative storytelling. Back-edge scientific research indicates that our magnificent cosmos, containing trillions of galaxies spanning billions of light years, might represent nothing more than a microscopic bubble drifting within an endless ocean of parallel dimensions. Every decision you've ever made, every quantum particle dancing through space at this instant, could be spawning countless branches of reality where different outcomes unfold simultaneously. Theoretical physicists working at the absolute forefront of human knowledge have uncovered mathematical evidence, suggesting something so revolutionary that it shatters every assumption our species has held about existence itself. Tonight we venture into territories where rigorous mathematics encounters the impossible, where laboratory discoveries point toward truths more extraordinary than any fictional universe ever conceived. This journey will guide us through breakthroughs that emerge from solving cosmic puzzles, where brilliant researchers wrestling with fundamental questions accidentally stumbled upon evidence for boundless worlds. These scientists weren't searching for alternate dimensions, they were attempting to understand why our reality appears so perfectly calibrated, why natural forces seem precisely tuned to permit stars, planets, and consciousness to emerge. The scientific foundation underlying our exploration rests on verified mathematics emerging from humanity's most profound understanding of quantum mechanics and cosmic evolution. Unlike fictional portrayals of parallel worlds, the concepts we'll examine arise naturally from equations successfully predicting observable phenomena in research facilities across the globe. These ideas represent logical extensions of physics already proven accurate through countless experiments and observations. Our expedition begins with acknowledging a humbling truth about human perception's boundaries. When nightfall reveals the stellar canopy above, you witness only an infinitesimally tiny sample of what actually exists throughout space. The cosmic horizon restricts our vision not due to atmospheric interference or technological constraints, but because of fundamental limitations imposed by light's finite speed and our universe's 13.8 billion year history. Imagine standing on any shoreline out to Earth's curvature prevents observing distant coastlines that certainly exist beyond the visible boundary. Similarly, cosmic expansion and light speed barriers create observational limits, concealing vast regions of space-time extending far beyond telescope detection capabilities. Within our observable domain exist roughly 2 trillion galaxies, each harboring hundreds of billions of stars surrounded by planetary systems potentially containing unimaginable diversity. According to emerging multiverse theories, this incomprehensibly enormous territory might constitute an infinitely small portion of total reality. Consider discovering that what appeared to be an entire ocean was actually just a microscopic water droplet within a boundless cosmic sea. This comparison barely captures the scale we're discussing, where our everything becomes essentially nothing compared to the complete picture. Scientific groundwork for these revolutionary concepts crystallized during the 1980s, when physicist Alan Guth addressed perplexing contradictions within Big Bang cosmology. Traditional models predicted our universe should display significant curvature and temperature differences across regions, yet observations revealed remarkable uniformity and flatness, seemingly violating basic physical principles. How could distant space areas that never communicated develop nearly identical characteristics? Guth's breakthrough solution introduced cosmic inflation (RAME), a brief exponential expansion period occurring during the universe's initial fractional seconds. Throughout this epoch, a region smaller than atomic particles expanded to cosmic proportions faster than light could travel. This rapid stretching eliminated initial irregularities while generating the flat, uniform cosmos we observe today. Detailed analysis of inflationary processes revealed something extraordinary and disturbing. Quantum fluctuations ending inflation in our cosmic region would produce different effects across other spacetime areas. While inflation terminated here, permitting matter and energy condensation into galaxies and stars, it would continue indefinitely elsewhere, eventually creating new inflationary domains destined for their own genesis events. This mechanism, called eternal inflation, suggests our universe represents merely one bubble within an endlessly expanding multiverse framework. New cosmic domains constantly emerge as quantum variations trigger inflation's cessation in different regions. Each bubble universe develops independently, creating unique physical laws and matter distributions completely isolated from all others. Andre Linde, among inflation theory's primary architects, describes this scenario using almost mystical terminology. Rather than a single cosmos governed by uniform physical principles, eternal chaotic inflation predicts a self-reproducing, perpetually existing multiverse where every conceivable possibility becomes realized somewhere across infinite domains. Meanwhile, in alternate dimensional bubbles, Earth's history unfolded along different trajectories. Perhaps asteroid impacts never eliminated dinosaurs, or entirely different evolutionary mechanisms produced life forms beyond current imagination. Mathematical frameworks supporting eternal inflation carry both beautiful and terrifying implications for understanding reality's true nature. If these theories prove accurate, everything capable of occurring will occur not simply once, but infinitely many times throughout the vast ensemble of bubble universes. Every possible atomic arrangement, every potential quantum outcome, every conceivable variation of physical constants becomes realized somewhere within multiverse structure. This connects directly to cosmology's most puzzling mystery, the fine-tuning problem. Nature's fundamental constants, from gravitational strength to electron mass, appear precisely calibrated to permit star formation, planetary development, and ultimately biological complexity. Modifying any values by minute amounts would create sterile universes incapable of supporting intricate chemistry required for life processes. Within single universe scenarios, such fine-tuning demands either extraordinary coincidence or intentional design. Throughout a multiverse populated by bubbles containing different physical properties, fine-tuning becomes natural selection. We observe life-permitting constants not because they were specially chosen, but because conscious observers could only evolve within universes where such conditions happen to exist. The vast majority of multiverse domains might remain empty and lifeless, but observers can only emerge within the tiny fraction where circumstances prove suitable for complexity and consciousness. This anthropic reasoning has generated intense debate among physicists, with some embracing it as elegant solutions while others view it as abandoning traditional scientific goals. The ramifications stretch far beyond academic research into domains of philosophy, spirituality, and human purpose. Some individuals find multiverse concepts liberating, indicating that our universe's apparent fine-tuning requires no special explanation or divine intervention. If all conceivable universes exist somewhere within the multiverse, then our particular combination of physical constants becomes ordinary mindshare, simply one possibility among infinite alternatives that happen to permit observers resembling ourselves. Others discover multiverse theories deeply disturbing, contending they drain significance from human existence by rendering our universe merely one among countless alternatives. If every possible version of history unfolds somewhere throughout the multiverse, then our decisions and behaviors lose their uniqueness and perhaps their importance. The concept of moral accountability becomes problematic when every conceivable choice gets realized within some parallel reality. These philosophical ramifications have captured attention from theologians, ethicists, and philosophers, wrestling with existence meaning within a potentially infinite multiverse. Some argue that multiverse theories remain compatible with religious worldviews, simply expanding creation's scope to encompass all possible realities. Others maintain that infinite multiverses eliminate divine creation necessity by making every possibility inevitable. Popular culture representations of multiverse concepts have also shaped public understanding and scientific discourse. Science fiction films, television programs, and novels routinely explore parallel dimensions and alternate realities, often diverging significantly from scientific multiverse theories. These fictional depictions can both inspire scientific interest and generate misconceptions about what multiverse theories actually predict. Hollywood's multiverse version typically involves transportation between parallel worlds, communication across dimensional barriers, and interactions between alternate versions of identical individuals. While dramatically captivating, these scenarios bear minimal resemblance to scientific multiverses, where different regions remain forever causally disconnected and inaccessible to direct observation or interaction. The disconnect between scientific and popular multiverse conceptions reflects broader challenges in science communication. Modern physics' mathematical sophistication makes conveying accurate scientific concepts to general audiences increasingly difficult, without significant simplification or distortion. This communication gap can produce public misunderstanding of what scientists actually study and claim to have discovered. Educational institutions are wrestling with incorporating multiverse concepts into curricula at various levels. Mathematical prerequisites for understanding eternal inflation or many worlds quantum mechanics are formidable, typically requiring advanced training in quantum field theory, general relativity, and mathematical physics. Yet these theories' philosophical implications are profound enough that they arguably deserve consideration within broader educational contexts. Some educators have developed approaches focusing on multiverse theory's conceptual and philosophical aspects, while minimizing mathematical complexity. These approaches emphasize critical thinking about evidence, scientific explanations, nature, and relationships between theory and observation. Students learn evaluating competing hypotheses and understanding challenges of testing theories invoking unobservable phenomena. Multiverse research's international character has also created new scientific collaboration models, transcending traditional institutional and national boundaries. The Planck satellite collaboration involved hundreds of scientists from dozens of countries pooling expertise and resources to achieve observational capabilities no single institution could accomplish independently. Similar collaborative models are being applied to gravitational wave detection, particle physics experiments, and theoretical research programs. These collaborative efforts reflect recognition that addressing fundamental questions about reality's nature requires resources and expertise, extending far beyond what individual researchers or institutions can provide. The multiverse, if it exists, operates on scales involving physics that challenge human understanding and technological capability limits. Understanding such phenomena requires global scientific community collective effort. Multiverse research's technological demands are also driving advances in computation, instrumentation, and data analysis, finding applications far beyond cosmology. Algorithms developed to search for subtle patterns in cosmic microwave background radiation are being adapted for medical imaging, climate modeling, and artificial intelligence applications. Precision instrumentation required for gravitational wave detection has spin-off applications in manufacturing, navigation, and fundamental metrology. Machine learning techniques originally developed for particle physics experiments are now being applied to analyze astronomical datasets for signs of multiverse interactions. These AI systems can identify patterns and correlations that human researchers might miss, potentially revealing subtle signatures of interactions between parallel realities that would otherwise remain hidden within cosmic noise. Quantum computing advances, motivated partly by testing many worlds interpretations, are yielding practical benefits in cryptography, optimization, and simulation of complex quantum systems. Even if these experiments never definitively prove parallel worlds' existence, they advance our understanding of quantum mechanics and its technological applications. Looking toward the future, several emerging technologies and experimental programs offer new possibilities for testing multiverse theories. The next generation of cosmic microwave background experiments will achieve unprecedented sensitivity to polarization patterns that might reveal signatures of quantum entanglement between universes. Ground-based telescopes with adaptive optics systems will map the universe's large-scale structure with extraordinary precision, potentially detecting subtle anomalies indicating interactions with parallel realities. Space-based gravitational wave detectors scheduled for the late 2020s and 2030s will probe frequency ranges inaccessible from Earth, potentially detecting primordial gravitational waves from cosmic inflation epochs. These observations could provide direct evidence for physical processes creating bubble universes in eternal inflation scenarios. Advanced particle physics experiments at the Large Hadron Collider and future colliders may discover evidence for extra dimensions or supersymmetric particles predicted by string theory. Such discoveries would strengthen theoretical frameworks naturally leading to multiverse scenarios, even without directly detecting other universes. Quantum computer development with thousands or millions of quantum bits may enable quantum mechanics tests probing boundaries between different interpretations. While these experiments may never definitively prove many worlds' interpretations, they could reveal quantum phenomena most naturally explained by parallel reality processing. Yet even as technology advances and experimental capabilities improve, the fundamental challenge of observing the unobservable remains. The multiverse, if it exists, may be structured in ways making empirical verification inherently impossible. Different eternal inflation regions remain causally disconnected by definition. Parallel quantum mechanics branches cannot communicate with each other without destroying quantum coherence that supposedly creates them. This observational limitation forces us to confront profound questions about relationships between physical reality and human knowledge. Can something be real if it can never be observed? How do we distinguish between mathematical consistency and physical existence? What criteria should we use evaluating theories transcending traditional empirical science boundaries? Some researchers have proposed that these questions reflect outdated scientific methodology conceptions emerging from studying macroscopic phenomena accessible to direct observation. Modern physics routinely deals with entities and processes that cannot be directly observed, yet remain scientifically valid through their observable consequences and mathematical consistency. The debate continues reshaping how we understand science's role in describing reality versus creating models that successfully predict observable phenomena. Whether multiverse theories represent genuine physics or sophisticated mathematics may ultimately depend on philosophical positions about knowledge, reality, and scientific explanation, rather than empirical evidence alone. From quantum fields to black hole interiors, the multiverse may simply represent humanity's next advancement in this progression toward theories describing reality beyond immediate experience's reach. Others maintain that abandoning empirical testability would fundamentally transform science's nature, converting it from an enterprise rooted in observation into something resembling mathematics or philosophy. They contend that preserving connections between theory and experiment remains essential for ensuring scientific knowledge stays relevant to understanding the natural world. This debate's resolution may ultimately depend on whether multiverse theories prove capable of generating successful predictions about observable phenomena, even if the multiverse itself remains unobservable. If eternal inflation correctly predicts cosmic microwave background fluctuation statistical properties, if many-world quantum mechanics enable superior quantum computing algorithms, and if string theory landscapes explain fundamental constant values, then these theories may earn acceptance through predictive success, rather than direct verification of their multiverse implications. Alternatively, future discoveries might reveal that our universe operates far more strangely than current multiverse theories suggest. Perhaps apparent fine-tuning of physical constants reflects deeper principles we haven't yet discovered. Perhaps quantum mechanics operates according to hidden variable theories eliminating parallel world necessity. Perhaps cosmic inflation was a singular event that didn't lead to eternal bubble production. Physics history overflows with theories that seemed compelling initially, but were eventually superseded by deeper understanding. The luminiferous ether, phlogiston theory, and steady-state cosmology all possess sophisticated mathematical formulations and seem to explain observed phenomena. Nevertheless, they were ultimately replaced by more accurate descriptions of natural processes. Multiverse theories may face similar fates, not because they're unobservable, but because they constitute incomplete or incorrect descriptions of physical reality. Future theoretical developments might reveal that what we interpret as evidence for multiple universes actually reflects more subtle aspects of a single extraordinarily complex cosmos. The search for understanding continues regardless of these uncertainties, driven by fundamental human desire to comprehend our place within existence's grand scheme. Whether the multiverse proves to be physical reality, useful mathematical tool, or interesting historical footnote in physics development, the questions it raises about reality's nature, observation, and scientific knowledge will continue challenging and inspiring researchers for generations ahead. As you drift through these final moments before sleep, consider that the very capacity to contemplate infinite realities represents something remarkable about consciousness and cosmos alike within a universe that may be just one among countless others. The ability to ask questions about existence, to wonder about parallel worlds, and to seek understanding through careful observation and mathematical reasoning becomes a precious gift connecting us to reality's deepest mysteries. The gentle rhythm of your breathing participates in quantum processes that some theories suggest create parallel worlds with each measurement and interaction. Your thoughts tonight might be branching across multiple realities, exploring different possibilities within the vast space of potential experiences that quantum mechanics seems to permit. Whether those parallel thoughts exist as physical realities or remain mathematical abstractions, they represent the universe's extraordinary capacity for complexity, beauty, and self-reflection through conscious observers resembling yourself. In contemplating the multiverse, we touch something infinite and profound, the mystery that may forever remain beyond complete understanding, yet continues inspiring our deepest curiosity about existence and nature and our remarkable place within it. Tonight, as consciousness fades into dream's quantum realm, where normal logic and causality rules relax, you join the ancient human tradition of wondering about realities beyond immediate experience. Questions that have kept physicists awake for decades now accompany you into sleep, where boundaries between possible and actual, between one universe and many, become beautifully, mysteriously permeable within the dreaming mind's theatre. Yet these theoretical frameworks, as elegant as they appear in mathematical formulation, face more fundamental challenges than mere observational difficulty. The question isn't simply whether we can detect other universes, but whether detection itself has meaning when applied to realities existing beyond all possible causal contact with our own. Dr. George Ellis of the University of Cape Town has spent decades wrestling with this conceptual puzzle, a distinguished cosmologist who worked alongside Stephen Hawking on space-time singularities mathematics. Ellis argues that multiverse theories blur crucial distinctions between what exists and what remains merely mathematically possible. From his perspective, physics must remain anchored to phenomena that can in principle influence observable reality. Ellis points out that scientific method developed precisely because it provided reliable ways to distinguish between accurate nature descriptions and appealing but incorrect ideas about world operations. By requiring theories make testable predictions, science avoided endless debates characterizing natural philosophy before controlled experimentation advent. But multiverse theories seem to sidestep this empirical constraint entirely. If other universes exist beyond all possible observation, then claims about their properties become unfalsifiable by definition. No conceivable experiment could prove that bubble universes don't exist, that quantum mechanics doesn't branch into parallel worlds, or that string landscape doesn't encompass infinite physical law variations. This unfalsifiability troubles many researchers who see it as departure from principles that made modern physics remarkably successful. Karl Popper's philosophy of science emphasized that genuine scientific theories must be capable of being proven wrong through observation. Theories that can accommodate any possible experimental result cease being scientific hypotheses and become metaphysical doctrines. Yet, multiverse research defenders argue that this criticism reflects overly narrow scientific methodology conceptions. They point out that many accepted modern physics features involve entities that cannot be directly observed. Black hole interiors lie beyond any possible observation, yet physicists confidently discuss what happens to matter crossing event horizons. Quarks cannot be isolated and studied individually, yet their existence receives universal acceptance based on indirect evidence. The key difference, critics respond, is that these unobservable phenomena still have observable consequences. Black holes affect nearby star and gas motion, allowing their properties to be inferred through gravitational effects. Quarks combine, forming protons and neutrons whose behavior can be studied thoroughly through particle accelerator experiments. Other universes, by contrast, seem defined precisely by their lack of observable consequences. If bubble universes were close enough to influence our cosmic evolution, they would cease being separate universes and become part of our extended cosmos. If parallel quantum worlds could communicate with our reality, they would collapse back into single quantum systems rather than remaining separate branches. This isolation appears fundamental rather than merely technological. No conceivable instrumentation advance could allow us to peer into other bubble universes or communicate with parallel quantum worlds. The theories themselves predict such contact is impossible, not just practically difficult, but logically contradictory. Dr. Jim Baggott, a science writer and former research scientist, has articulated this concern in particularly stark terms. He argues that multiverse theories represent physics crisis where mathematical elegance has become divorced from empirical reality. From his view, the field drifts toward what he calls fairy tale physics, where beautiful mathematical structures get mistaken for natural world descriptions. Baggott's critique extends beyond multiverse theories to encompass what he sees as broader theoretical physics trends toward increasingly abstract and untestable speculation. String theory, supersymmetry, and extra dimensions all suffer similar problems, he argues, creating elaborate mathematical edifices with little connection to observable phenomena. The concern isn't merely academic. Physics departments worldwide train graduate students to work on multiverse theories, quantum gravity, and string cosmology. Talented young researchers dedicate careers to problems that may have no solution, or worse, no meaningful connection to physical reality. Meanwhile, other physics areas that could yield practical benefits receive less attention and resources. Climate physics, condensed matter research, and plasma physics all offer opportunities to address pressing human needs while advancing fundamental understanding. Multiverse research opportunity cost may be measured not just in abstract knowledge, but in concrete applications that could improve human welfare. Yet this utilitarian argument faces its own challenges. Physics history overflows with apparently abstract investigations that later yielded unexpected practical applications. Einstein's general relativity seemed like pure mathematical speculation when first proposed, yet it now enables GPS satellites that guide modern navigation. Quantum mechanics emerged from attempts to understand atomic spectra, but eventually revolutionized electronics and computing. The search for ultimate truth continues, whether through multiverse exploration or more empirically grounded investigations, driven by humanity's insatiable curiosity about existence's deepest mysteries and our extraordinary place within the cosmic story that continues unfolding around us. Awareness doesn't arise from material mechanisms, but represents self-conscious mathematical frameworks examining their own logical coherence. This mathematical cosmos hypothesis challenges boundaries of what most physicists willingly embrace. Even investigators sympathetic to multiverse concepts often discover Tegmark's perspective too extreme, too separated from anything resembling empirical research. Nevertheless, his reasoning flows logically from assumptions that numerous physicists do accept, illuminating conceptual difficulties that emerge when we attempt comprehending relationships between mathematics and physical existence. Consciousness questions become particularly bewildering within multiverse contexts. If every conceivable arrangement of matter and energy exists somewhere throughout the multiverse, then aware observers resembling ourselves exist in innumerable variations across different realities. Some versions might differ only through trivial details, while others might possess completely alternative sensory encounters or cognitive abilities. This multiplicity of conscious observers generates profound inquiries about personal identity and subjective experience's essence. Are you identical to your duplicate counterparts throughout other dimensions? If your awareness branches with every quantum measurement, which branch represents authentic you, do all possible versions of yourself maintain equal claims to being genuine, or exists something special about the particular branch you happen to encounter? These inquiries extend beyond philosophy into practical considerations about decision-making and moral accountability. If every conceivable choice you might execute gets realized somewhere throughout the multiverse, do your individual selections matter? Several philosophers contend that moral responsibility becomes meaningless within a multiverse where every possible action occurs regardless of your personal decisions. Others maintain that this reasoning commits category errors by confusing what happens throughout the entire multiverse with what matters from your particular viewpoint as a conscious observer. Even if all possible versions of your life unfold somewhere throughout the multiverse, you can only encounter one branch directly, making your choices significant from your own subjective perspective. Many worlds' interpretation of quantum mechanics encounters similar conceptual difficulties. If consciousness divides with every quantum measurement, generating parallel versions of yourself that encounter different outcomes, why do you seem to encounter only one definite reality, rather than superposition of all possibilities? Several researchers have suggested that consciousness itself might function in selecting which quantum reality branch becomes encountered. This concept connects to older quantum mechanics, interpretations that emphasize observation's function in determining physical outcomes. However, it also generates difficult inquiries about what constitutes consciousness and how mental mechanisms could influence quantum evolution. Dr. Roger Penrose and Dr. Stuart Hameroff have created among the most detailed theories connecting consciousness to quantum mechanics. They suggested that microtubules within brain cells might maintain quantum coherence at body temperature, allowing consciousness to emerge from quantum computational mechanisms spanning multiple parallel realities. While their orchestrated objective reduction theory remains controversial among neuroscientists, it demonstrates how seriously several researchers consider connections between consciousness and quantum multiverse contexts. If consciousness does emerge from quantum mechanisms, then subjective experience's nature might be intimately connected to parallel reality's structure. Experimental evidence searches continue despite these conceptual difficulties. Most promising near-term possibilities involve testing theoretical frameworks that predict multiverse contexts rather than directly detecting other dimensions. If eternal inflation theory, many worlds quantum mechanics, or string theory can undergo validation through other means, then multiverse implications gain credibility even without direct confirmation. The Large Hadron Collider continues probing matter's fundamental structure at unprecedented energies, searching for evidence of extra dimensions, supersymmetric particles, or other exotic phenomena predicted by theories naturally leading to multiverse contexts. While no definitive discoveries have emerged yet, ongoing experimental programs continue constraining theoretical possibilities and could potentially reveal physics supporting multiverse predictions. Future particle accelerators with even higher energies might probe deeper into reality's fundamental structure, potentially accessing energy scales where string theory effects become apparent, or where extra dimensions required by multiverse contexts begin manifesting. These experiments represent among humanity's most ambitious attempts understanding physical reality's deepest levels. Cosmological observations also continue advancing with increasingly sensitive measurements of cosmic microwave background, gravitational waves, and large-scale structure, providing new windows into the early universe. Recently launched James Webb Space Telescope already reveals unprecedented details about first galaxy formation, potentially preserving information about cosmic inflation processes that might have created our bubble dimension. European space agency's planned LISA gravitational wave detector will operate in space, providing access to gravitational wave frequencies that cannot be observed from Earth. These space-based observations might detect primordial gravitational waves from cosmic inflation, providing direct evidence for physical processes that multiverse theories invoke, explaining our cosmic origins. Advanced ground-based gravitational wave detectors, like proposed Einstein telescope, could achieve sensitivities, allowing detection of gravitational waves from phase transitions in early universe, cosmic string networks, or other exotic phenomena associated with multiverse contexts. These observations would probe physics at energy scales and time periods that cannot be accessed through any other means. Quantum technology continues advancing as well, with increasingly sophisticated quantum computers and quantum communication systems providing new ways testing quantum mechanics foundations. While these experiments may never definitively prove many worlds' interpretation, they continue revealing quantum reality's strange and counterintuitive nature. Several researchers have proposed that advanced quantum computers might eventually become capable of detecting interference effects between different quantum reality branches, providing indirect evidence for parallel worlds. While such experiments remain speculative, they demonstrate how technological progress continues opening new possibilities for testing fundamental theories about reality's nature. International collaboration required for these advanced experiments continues strengthening, with researchers from dozens of countries contributing to projects like Large Hadron Collider, LIGO gravitational wave detection, and cosmic microwave background analysis. This global cooperation reflects recognition that understanding fundamental questions about reality requires resources and expertise transcending national boundaries. Educational institutions also grapple with incorporating multiverse concepts into physics curricula. Mathematical sophistication required understanding eternal inflation, many worlds quantum mechanics, and string theory landscapes present significant pedagogical challenges. Nevertheless, these theories' philosophical implications are profound enough that they arguably deserve consideration within broader educational contexts. Several educators have developed approaches emphasizing scientific methodology used evaluating multiverse theories rather than theories' detailed mathematics themselves. Students learn critical thinking about evidence, scientific explanation, nature, and theory observation relationships, while engaging with some of contemporary physics' most profound questions. Whether multiverse theories ultimately prove correct or incorrect, they have already transformed how we think about reality, scientific knowledge, and humanity's place within existence. They challenge us to consider possibilities extending far beyond direct experience while maintaining connection to rigorous mathematical reasoning and careful observation. The journey into multiverse exploration represents something fundamentally human, might as our curiosity about what might be possible, our desire to understand our cosmic context, and our willingness to follow mathematical logic wherever it leads, even into realms that stretch imagination beyond familiar boundaries. Students develop critical thinking regarding evidence verification and connections between mathematical coherence and physical existence. These abilities remain valuable regardless of whether multiverse concepts ultimately prove accurate. Popular culture representation of multiverse ideas continues evolving as well, with science fiction films and television programs exploring increasingly sophisticated versions of parallel reality scenarios. While these fictional depictions often diverge significantly from scientific multiverse concepts, they help sustain public fascination with fundamental inquiries about reality's essence and our cosmic position. Science museums and planetariums worldwide have created exhibitions attempting to convey multiverse theories' wonder and complexity to general audiences. These educational efforts confront challenges of making abstract mathematical ideas accessible while preserving scientific precision and avoiding oversimplification. Economic implications of multiverse investigation extend beyond direct scientific applications. Technological advances required for testing multiverse concepts drive innovation in areas like precision instrumentation, data analysis, and high-performance computing, finding applications throughout the economy. International collaborations fostered by multiverse investigation also strengthen scientific and technological connections between nations. Several private organizations have begun investing in multiverse-related investigation, recognizing its potential for advancing fundamental comprehension and driving technological innovation. The Templeton Foundation has funded numerous projects exploring multiverse theory's philosophical implications, while technology companies have supported quantum computing investigation that could eventually test many worlds' interpretations. Looking toward tomorrow, several emerging technologies and experimental programs offer new possibilities for testing multiverse concepts. Quantum computing advances may enable simulations of cosmological scenarios too complex for classical computers, potentially revealing new insights into eternal inflation and bubble universe formation. Machine learning and artificial intelligence techniques are being applied to analyze vast astronomical data sets for subtle patterns that might indicate multiverse interactions. These AI systems can process enormous amounts of information with superhuman speed and accuracy, potentially discovering signatures that human researchers would miss. Development of space-based telescopes with unprecedented sensitivity and resolution will provide new windows into the early universe and cosmic large-scale structure. These observations might reveal anomalies or patterns supporting multiverse predictions, though they could equally well reveal phenomena challenging current theoretical frameworks entirely. Advanced materials investigation might eventually enable construction of gravitational wave detectors with sensitivity far beyond current capabilities, potentially detecting signals from cosmic history's earliest moments when multiverse-generating processes might have been active. Similarly, advances in quantum sensor technology could provide new ways probing space and time's fundamental structure. Yet even as technology advances and experimental capabilities improve, fundamental conceptual challenges surrounding multiverse theories remain. Questions about what constitutes scientific knowledge when dealing with potentially unobservable phenomena continue generating debate among physicists, philosophers, and educators. Several researchers are exploring alternative approaches to these conceptual challenges, developing new frameworks for understanding relationships between mathematical models and physical reality. These approaches might eventually provide ways of evaluating multiverse theories that don't depend on direct observational confirmation of other dimensions. Others are investigating whether multiverse theories might make subtle but testable predictions about observable phenomena that haven't yet been recognized. Perhaps statistical properties of cosmic structure, quantum system behavior, or fundamental constant values contain hidden signatures of multiverse physics that future analysis might reveal. The possibility also remains that multiverse theories are simply incorrect, interesting mathematical exercises that don't correspond to physical reality. Future theoretical developments might reveal more elegant explanations for apparent fine-tuning, quantum measurement, and cosmic inflation that don't require invoking unobservable parallel realities. Alternatively, entirely new physics might emerge transcending current multiverse scenarios while preserving their most successful predictions. Science history overflows with theoretical frameworks that seemed comprehensive initially, but were eventually superseded by deeper understanding incorporating their insights while revealing new complexity layers. Understanding searches continue regardless of these uncertainties, driven by fundamental human desire to comprehend our place within existence's grand scheme. Whether multiverse theories prove representing genuine insights into reality's nature or interesting detours in physics history, they have already contributed to expanding our conception of what might be achievable. In pushing scientific thinking boundaries, multiverse investigation has forced physicists to confront fundamental questions about observation, explanation, and human knowledge limits. These conceptual challenges have value independent of whether other dimensions actually exist, strengthening our understanding of scientific method and its proper application to phenomena stretching empirical investigation limits. Mathematical techniques developed for multiverse investigation have found applications throughout theoretical physics, from condensed matter systems to black hole physics to quantum information theory. International collaborations fostered by multiverse investigation have strengthened scientific cooperation and created new models for addressing complex interdisciplinary problems. Perhaps most importantly, multiverse theories have inspired a new generation of physicists to think boldly about reality's nature and push against conventional boundaries in their search for understanding. This willingness to explore radical possibilities while maintaining rigorous evidence standards represents scientific inquiry's best tradition. As you settle into quiet moments before sleep, consider that the very capacity to contemplate infinite realities represents something remarkable about consciousness and its relationship to the cosmos. Whether those realities exist as physical entities or mathematical abstractions, the ability to conceive them reflects human thought's extraordinary power to transcend experience's immediate boundaries. The gentle rhythm of your breathing connects you to quantum processes that some theories suggest create branching realities with each interaction. Your thoughts tonight might explore possibilities spanning multiple dimensions, touching questions that have puzzled humanity since we first looked up at stars and wondered what lies beyond the visible horizon. In contemplating the multiverse, we participate in an ancient human tradition of seeking to understand our place in existence. Questions that drive multiverse investigation: why does the universe have the properties it does? Are we alone in the cosmos? What is reality's nature itself? Echo philosophy and religion's deepest concerns, while requiring mathematical physics precision and rigor. Whether the multiverse exists as described by current theories, whether it takes forms we haven't yet imagined, or whether reality proves to be something entirely different, the search for understanding enriches our appreciation of existence and our role as conscious observers in a cosmos that may be far stranger and more wonderful than we can currently comprehend. Tonight, as your consciousness drifts into dreams where the ordinary rules of logic and physics soften into possibility, remember that you carry within your mind the same curiosity that drives humanity's greatest discoveries. The questions we've explored together, and amount about infinite worlds, parallel selves, and the deepest nature of reality, will continue inspiring generations of researchers to push beyond the known into realms where mathematics meets mystery. In the end, perhaps the multiverse's greatest gift isn't proof of other worlds, but the expansion of human imagination and the recognition that reality might be far more magnificent than we ever dared to dream. Whether we discover definitive answers or uncover even deeper mysteries, the journey itself transforms our understanding of what it means to exist, to wonder, and to seek truth in a universe that continues revealing new layers of astonishing complexity. The search continues, driven by our endless fascination with existence itself and our remarkable capacity to ask questions that stretch beyond the boundaries of direct experience into the infinite realm of possibility that consciousness makes available to us all. Tonight, as awareness dissolves into sleep's domain where boundaries between achievable and real become magnificently fluid, you participate in humanity's continuing dialogue with mystery itself. Inquiries about parallel dimensions and boundless universes that have confronted physicists for decades now escort you into slumber, where ordinary logic and causality constraints soften, permitting the mind to investigate possibilities that may eternally remain beyond scientific observation's grasp, yet persist in inspiring our most profound amazement about existence essence and our exceptional position within it. The tender darkness enveloping you tonight isn't vacant, but overflowing with possibilities extending beyond anything our ancestors could have envisioned. Each starlight photon reaching your vision has journeyed across immense distances, conveying information from cosmic eras when the universe was youthful and peculiar. Nevertheless, even this ancient illumination represents merely the most minute fraction of what might actually exist beyond our perception's limits. The observable cosmos, that reality sphere we can actually detect and examine, extends roughly 46 billion light-years in every direction from Earth. This might seem impossibly enormous, containing as it does over 2 trillion galaxies, each sheltering billions of stars. But here's where the narrative becomes truly extraordinary. Beyond this cosmic boundary lies something challenging our most fundamental assumptions about existence's very nature. Consider it this way. When you stand on a shoreline and gaze toward the ocean, your view gets restricted by Earth's curvature. You know there's additional ocean beyond what you can perceive, but the horizon establishes a natural boundary to your observation. Our cosmic situation proves remarkably similar, except the horizon isn't established by planetary geometry, but by light's fundamental speed and our universe's finite age. This realization has guided cosmologists to contemplate among the most profound inquiries in all science. If we can only observe a finite space region, what exists beyond? The answer, according to several of our most brilliant theoretical physicists, might be far stranger than even the most imaginative science fiction has dared to propose. Dr. Alan Guth was working late in his office at Stanford Linear Accelerator Center in December 1979 when he scribbled a note in his laboratory notebook that would forever transform how we think about cosmic origins. The word spectacular appears in capital letters, circled emphatically next to calculations that would eventually lead to among the most revolutionary concepts in modern cosmology. Guth had been wrestling with several troubling problems in Big Bang theory. Why was the universe so remarkably flat when basic physics suggested it should be curved? Why did space regions that had never been in causal contact show nearly identical temperatures? The solutions emerging from his calculations seemed almost too elegant to be accurate. His proposal was called cosmic inflationis, the concept that in the first tiny fraction of a second after the Big Bang, space itself underwent exponential expansion. During an interval shorter than the time it takes light to cross a proton, a region smaller than a subatomic particle expanded to dimensions larger than a grapefruit. This stupendous stretching would smooth out any initial irregularities and establish the flat, uniform universe we observe today. But inflation theory contained within it the seeds of something even more remarkable. The same quantum fluctuations that drive inflationary processes don't terminate everywhere simultaneously. While inflation stops in some regions, allowing matter and energy to condense into galaxies and stars, it continues elsewhere, establishing new domains that undergo their own inflationary epochs. Dr. Andrei Linde, working independently at Lebedev Physical Institute in Moscow, developed this insight into what became known as eternal inflation. In his chaotic inflation model, the universe becomes a self-reproducing system where new regions constantly branch off from inflating domains, each eventually undergoing its own Big Bang-like transition when inflation ends locally. Envision a vast ocean where bubbles constantly form and expand. Each bubble represents what we might call a universe, complete with its own space, time, matter, and energy. Our observable cosmos would be just a tiny region within one such bubble, while countless other bubbles expand and evolve according to their own physical laws throughout the eternal sea of inflating space. Linde describes this scenario with almost poetic wonder. Instead of a universe with a single set of physical laws, eternal chaotic inflation predicts a self-reproducing, eternally existing multiverse where every possibility that quantum mechanics allows eventually becomes realized. Somewhere in this vast ensemble of bubble universes, he suggests, another version of you is contemplating these very same concepts, perhaps reaching different conclusions about their implications. The mathematics underlying eternal inflation are both beautiful and unsettling in their scope. If the theory proves correct, then everything that can happen will happen not just once, but infinitely many times across the boundless collection of bubble universes. Every possible atomic arrangement, every potential quantum event outcome, every conceivable variation of physical constants gets actualized somewhere in the multiverse. This connects to among the most perplexing puzzles in all physics memory is what researchers call the fine-tuning problem. Nature's fundamental parameters, from gravity's strength to the electron's mass, appear calibrated with extraordinary precision to permit star, planet, and ultimately life formation. Consider the cosmological constant empty space's energy density that drives our universe's accelerating expansion. Quantum field theory suggests this quantity should be enormous, roughly 10 to the 120th power, times larger than what we actually observe. This represents perhaps the worst theoretical prediction in science history. Yet somehow our universe ended up with a cosmological constant so small it allows galaxies to form and persist. Change this parameter by even a tiny amount, and the consequences would be catastrophic. A slightly larger value would cause space to expand so rapidly that matter could never clump together into cosmic structures. A negative value of similar magnitude would cause the entire universe to collapse before stars could ignite and burn. The same delicate balance appears throughout fundamental constants. Increase the strong nuclear force's strength by just 5%, and hydrogen would be unstable, preventing water and organic chemistry formation. Decrease it by the same amount, and nuclear fusion in stellar cores would shut down, leaving the universe cold and dark. Elementary particle mass ratios, the four fundamental forces' relative strengths, even spatial dimension numbers all seem precisely tuned to permit complexity and life. In a single universe scenario, this fine-tuning appears to require either extraordinary coincidence or intelligent design. The probability that all these parameters would randomly fall within life-permitting ranges is so vanishingly small that it challenges credibility. Yet eternal inflation provides an elegant alternative explanation through what physicists call the anthropic principle. If different multiverse regions have different values of these fundamental constants, then fine-tuning becomes a selection effect rather than a cosmic mystery. We observe life-permitting parameters not because they were specially chosen, but because we could only have evolved in a region where such parameters allow for our existence. The vast majority of bubble universes might be sterile and lifeless, but observers can only emerge in the tiny fraction where conditions happen to support complexity. Steven Weinberg demonstrated this anthropic reasoning's power in the 1980s, when he used multiverse arguments to predict the cosmological constant's value years before it was measured. His calculations suggested the constant should be small but positive, just barely consistent with galaxy formation. As you drift into sleep tonight, surrounded by the gentle darkness filled with infinite possibilities, remember that your capacity to contemplate these cosmic mysteries represents something extraordinary about consciousness itself. Whether parallel worlds exist as physical realities or remain mathematical abstractions, the ability to conceive them reflects human thought's remarkable power to transcend immediate experience and touch the deepest questions about existence. The search for understanding continues, driven by our endless curiosity about what might be possible in a cosmos that may be far stranger and more magnificent than we can currently comprehend. In dreams, where logic softens and imagination soars, you join the eternal human quest to understand our place in the grand cosmic story that unfolds around us, whether in one universe or infinitely many. When distant supernova observations confirmed cosmic acceleration in the 1990s, Weinberg's anthropic prediction proved remarkably precise. This success has inspired researchers to apply similar reasoning to other fine-tuning problems, though not without controversy. Critics contend that anthropic explanations are inherently retrospective, designed to explain existing observations rather than make genuine predictions about new phenomena. They worry that accepting such reasoning could guide physics away from its traditional goal of discovering unique testable theories toward a more speculative enterprise that explains everything, while predicting nothing specific. Meanwhile, quantum mechanics offers its own pathway to multiple realities through an interpretation that eliminates one of the theory's most puzzling features. Since quantum physics' early days, researchers have grappled with the measurement problem. Why do particles exist in multiple states simultaneously until observed, at which point they mysteriously collapse into single definite properties? Hugh Everett III proposed a radical solution in his 1957 doctoral thesis at Princeton University. Rather than accepting that quantum measurements cause wave function collapse, Everett suggested that all possible outcomes actually occur simultaneously in parallel branches of reality. This many-worlds interpretation eliminates the arbitrary boundary between quantum and classical physics by treating everything as fundamentally quantum mechanical. In Everett's vision, every quantum interaction throughout the universe constantly splits reality into multiple branches. Each possible outcome of every quantum measurement gets realized in a different branch, creating an ever-proliferating tree of parallel worlds. These worlds are completely real but forever isolated from one another, making direct communication or travel between them impossible. Dr. David Deutsch of Oxford University has become among the most eloquent advocates for many worlds interpretation, connecting it to quantum computation and information theory. He argues that quantum computers derive their extraordinary power from performing calculations across multiple parallel worlds simultaneously, harnessing multiverse computational resources to solve problems that would be intractable for classical systems. When a quantum computer processes information, Deutsch suggests it isn't just manipulating quantum bits in our reality, but coordinating calculations across countless parallel versions of itself. The final answer emerges from a kind of quantum democratic process where different branches explore different solution paths before converging on the result that appears in our particular world. The scale of branching in many worlds interpretation is truly staggering. Dr. Max Tegmark of MIT calculates that parallel world numbers grow exponentially with each passing moment, as every quantum transition throughout the observable universe creates new branches. Every atomic decay, every photon absorption, every neural firing in your brain right now potentially splits reality into multiple versions where slightly different outcomes occur. This quantum multiverse operates on completely different principles than eternal inflation's bubble universes. While inflating domains are separated by physical space and might evolve under different physics laws, quantum mechanics' parallel worlds are superimposed in identical space, but isolated by quantum reality's fundamental structure itself. They represent different branches of the universal wave function, each as complete and real as our own experienced reality. String theory contributes yet another multiverse vision through what researchers call the landscape of possible universes. This ambitious theoretical framework attempts unifying all fundamental forces by describing particles as tiny vibrating strings rather than point-like objects. But string theory requires additional spatial dimensions beyond the three we observe, and these extra dimensions must be compactified in ways remaining hidden at everyday scales. Dr. Leonard Susskind of Stanford University has explored dimensional compactification implications in extraordinary detail. String theory's mathematical complexity allows for astronomical numbers of ways to curl up extra dimensions, each leading to different physical laws and constants in the resulting four-dimensional universe. Current estimates suggest possible configuration numbers could exceed 10 to the 500,000th power. When combined with eternal inflation, string landscape suggests that different multiverse regions settle into different string theory configurations, creating bubble universes with dramatically different physical properties. Some might have stronger or weaker forces, different numbers of particle types, or even entirely different dimensional structures. This provides another potential explanation for our universe's apparent fine-tuning, with all possible physical constant values being realized somewhere across the vast landscape of possibilities. Yet despite decades of theoretical development and increasingly sophisticated mathematical frameworks, the multiverse remains among modern physics' most contentious ideas. The fundamental challenge is observational. By definition, other universes exist beyond our cosmic horizon, or in parallel quantum branches we can never directly access. This apparent untestability has led some critics to argue that multiverse theories venture beyond legitimate science into metaphysical speculation. Dr. Paul Steinhardt, among inflation theory's original architects, has become among the most vocal critics of eternal inflation and its multiverse implications. He argues the theory has become unfalsifiable and therefore unscientific, capable of accommodating any possible observation by invoking appropriate multiverse regions. The debate touches fundamental questions about scientific knowledge as nature itself. Traditional science approaches emphasize testable predictions that can undergo verification or falsification through observation and experiment. But multiverse theories appear to violate this principle by making claims about entities that may be fundamentally unobservable. Several physicists have responded by developing new criteria for evaluating theories that cannot undergo direct testing. They focus on explanatory power, mathematical consistency, and ability to make predictions about observable phenomena, even when theories invoke unobservable entities. Others remain deeply skeptical, arguing that without empirical contact, these ideas cease being physics and become something closer to philosophy or mathematics. Evidence searchers have led scientists to examine subtle patterns in cosmic microwave background radiations, that ancient Big Bang afterglow filling all space. Researchers have sought signatures that might indicate collisions with other bubble universes, unusual correlations that might suggest quantum entanglement between different realities, or statistical anomalies deviating from single universe predictions. Dr. Stephen Feeney and colleagues at University College London made headlines when they claimed discovering circular patterns in this primordial radiation that could represent scars from encounters with neighboring universes. Analysis proved extraordinarily complex, requiring sophisticated algorithms to separate potential multiverse signatures from instrumental noise and astrophysical contamination. While initial results seemed promising, more detailed analysis using European Space Agency's Planck satellite data failed, confirming claimed detections. Patterns that had appeared significant dissolved into statistical noise when examined with greater precision, illustrating the extraordinary difficulty of detecting phenomena existing at observational capabilities' very limits. Similar challenges have confronted other multiverse evidence attempts. The cosmic microwave background cold spot, an unusually large and frigid region in southern sky, has been proposed as possible signature of interaction with another universe. Yet conventional explanations involving cosmic voids and gravitational effects remain favored by most researchers. Stakes in this debate couldn't be higher. If multiverse theories are correct, they would fundamentally transform our reality understanding, suggesting our observable universe represents just one thread in existence's infinite tapestry. Every question about why the universe possesses its properties would need reframing through observer selection effects across reality ensembles. But implications extend beyond abstract philosophy into practical questions about how science should proceed. If we accept that some reality aspects may forever remain beyond direct observation, how do we maintain scientific rigor? How do we distinguish between legitimate theoretical speculation and untestable metaphysics? The multiverse remains among science's most beautiful and bewildering frontiers, where rigorous mathematics meets existence's deepest questions. Whether these parallel realities emerge from eternal inflation, quantum branching, or string theory's vast landscape, they challenge us to expand our conception of what might be possible while maintaining careful skepticism, defining genuine scientific inquiry. Tonight, as you drift towards sleep, remember you are part of humanity's grandest adventure, the quest to understand our place in a cosmos that may be far stranger and more magnificent than we ever dared imagine. In dreams where possibilities multiply and logic softens into wonder, you join countless others across time who have gazed at stars and asked the eternal questions that define us as conscious beings. Whether the multiverse exists as physical reality or mathematical abstraction, contemplating it expands our sense of wonder and connects us to mysteries that may forever inspire human curiosity. Sleep well, fellow traveler, in the infinite mystery we call reality, knowing that tomorrow brings new opportunities to explore questions that stretch our understanding toward horizons we're only beginning to glimpse. Sweet dreams in the quantum realm of sleep, where your consciousness might just touch possibilities that exist beyond the boundaries of ordinary experience.